Hello, this begins our discussions on topics in Chapter 5. The first topic we'll discuss is extended precision operations. Up to this point, we've only used data that was either 8-bit or 16-bit wide. But what about data that's 32-bit wide or 64-bit wide or wider? How do we do operations on that? Well, we'll get started with 32-bit wide data. We're going to use this data type here, or uint32. As with these previous two types, this explicitly declares the width of the data. In our C compiler that we're using for the PIC24, this will be declared as an unsigned long, while the uint16 would be declared as an unsigned int. One problem with using these data types instead of these is that the size of the int and long depends on the C implementation. With some machines, both an int and a long are 4 bytes, with a short, an unsigned short, being 2 bytes. On some machines, a long is 8 bytes. By using these data types here, we unambiguously declare what the width of a particular variable is. Let's look at a form of the move instruction that supports a 32-bit data move. Move.d, where D stands for double word, will move the double word beginning at a source working register to a destination working register. This source working register can also include an indirect addressing mode. So this will move from working register S and S plus 1 to destination register WND and WND plus 1. This moves in the other direction. This will move from a working register source to a destination register, where this can be a indirect mode. Using an indirect mode for here can allow us to move from working registers to memory. Using an indirect mode here can allow us to move from memory to a working register. Let's take a look at an example. This is going to be move.d W0 to W2. This is going to move the 32-bit values that are stored in W0 and W1 to the register pair W2 and W3. So after execution, W2 will have in it 1A23 and W3 will have in it 0800. Both of these addressing modes are register direct. If you use a register direct addressing mode, the register number must be an even number. This does a register to register copy. Let's do a memory to register copy. This addressing mode is going to be register indirect. For a register indirect, this working register can be any register, W0 to W15. Remember that register indirect, it treats the value in the register as an address. So this is going to say the start of our effective address is going to be 0800. So this is going to say move the double word beginning at 800, which is going to be 800 and 802, and move that to this register direct register pair, which is going to be W2 and W3. So we're going to look at location 800, which is going to have a 90B3. That's going to be moved to W2. The 16-bit word 4E81 at 802 is going to be moved to W3. Let's look at some 32-bit values in C. Here we're going to specify two 32-bit variables, K and P. We'll use the type uint32. So in the MP lab, we have to declare K as being .4. This is going to take 4 bytes. P will also be declared as .4. Now let's initialize K to this 32-bit value 76543210. So first thing that we're going to do is we're going to take the least significant word here, 3210, as an immediate, move that to W0, then move that W0 to K. Then we're going to take the most significant word, 7654, move it to W0, then move that to K plus 2. So this is the first time we've seen this. What does K plus 2 mean? Recall that K is a label. K stands for an address. Let's assume that K was actually at memory location 800. Then K plus 2 is going to stand for 802, which is going to be the most significant word of this 32-bit value. So all this is saying is computing an address that we're going to use for this move. Now let's take a look at this assignment statement here, in which we're going to move K to P. We're going to copy the K 32-bit word in K to P. So here's what we're going to do. We're going to first do the least significant word. We're going to move K to W0. Then we're going to copy W0 to P. We're going to move the most significant word at K plus 2 to W0. Then move that to P plus 2. In these assignment statements, it doesn't matter the order in which we assign the words, least significant word first or most significant word first. We could have reversed the order of these operations. We could have done this first and then done that second. It would not have affected this code. Notice that if this would have been 16-bit wide variables, this would have only been 2 bytes, and we only would have needed 2 instructions for this move and 2 instructions for this move. So when dealing with 32-bit data, you're going to use twice as much memory space, and you're going to generally take twice as many instructions to accomplish the operations. What this means is that you should only use 32-bit variables if you need the extended range that the extra bits give you. Now let's do a 32-bit bitwise logical operation. This statement here says K is equal to K bitwise ANDed with J, where both of these are 32-bit wide variables. The first thing we'll do is the least significant word operation. We're going to do a move J to W0. That's going to take the least significant word of J and move it into W0. Because the PIC24 uses little endian order for storing bytes, the least significant word is stored in the first 2 bytes, and the most significant word is stored in the next 2 bytes. We're then going to do an AND K. This is going to take the least significant word of K, and that with the value in W0, which happens to be J dot least significant word as done by this instruction, and it's going to put the result back into K. The next 2 instructions will then do the most significant word. So it's going to move J plus 2, which represents the address of the most significant word of J, into W0. And then we'll do AND K plus 2, which will take the most significant word of K, and it with W0, which happens to have the most significant word of J, and write that result back to K, most significant word. The order in which the word operations are done, either least significant word first or most significant word first, for bitwise logical operations do not matter. We could have executed these 2 instructions before these 2 instructions, and we would have gotten the same result. Let's talk about 32-bit addition and subtraction. In this case here, we're going to be adding this 32-bit value to this 32-bit value. We need to do it 16 bits at a time. So we're going to take the least significant word here and add that to this least significant word and produce this result. When we do this add, we're going to get a carry out here. That carry needs to be added to the sum of the most significant word plus this most significant word. So when we do an addition here, we're going to need to somehow include this carry from the least significant word. When we're doing subtraction, we need to do this, essentially the same thing. We're going to do the subtraction 16 bits at a time, but we'll do the least significant bit word subtraction first. If there's a borrow from the most significant word, then when we do the subtraction of the most significant word, we're going to need to include somehow this borrow in the subtraction operation. When we do addition and subtraction, we need to do the least significant word first, followed by most significant word. It does matter the order in which we do these 16-bit operations. So let's look at some examples. We're going to do 32-bit addition and subtraction. So here's going to be K is equal to K plus J. These are 32-bit wide variables. This 2 instruction sequence right here will add the 2 least significant words together by moving J to W0 and then doing an add of K. This 2 instruction sequence right here is going to do the most significant word addition, except we're going to use a different add instruction here. We're going to use an add with carry. An add with carry will add this 16-bit value plus this 16-bit value, but it will also add in whatever the value of the carry flag is. Well, what is the value of the carry flag? What carry flag are we going to be adding in? We're going to be adding in the carry that was produced by this add instruction here. This form of the move instruction here affects none of the flags. So whatever carry was produced by this add is still going to be the same carry value when we do this add with carry. So when adding 32-bit values, we'll use the normal add instruction for the least significant word addition, and then we'll use an add with carry for the most significant word addition. For subtraction, we'll do this. Let's look at this example. We'll do P is equal to P minus Q. These are 32-bit wide variables. This two instruction sequence right here will subtract the Q least significant word from the P least significant word and store the result back into P. This one right here will do the same for the most significant word. We're gonna use a different subtract instruction. We'll use a subtract with borrow. Like the add with carry, this is going to take into account one additional factor. It's going to include the borrow into this subtraction. What borrow are we including? We're including the borrow that was produced by this subtract operation right here. Here are some other forms of add with carry, subtract with borrow. Here are some forms for subtract with borrow. Reverse. What reverse subtraction means is that recall subtraction here does WB minus WS. This is going to do reverse. It's going to say WS minus WB. There's also some compare with borrow forms. We'll use these when we're comparing 32-bit operations. These operations is said to be sticky in terms of the Z flag, in that it can only be cleared by these instructions. We'll talk more about what this actually means on the next slide. Note that there is no compare against 0 or borrow instruction. Let's talk about the Z flag behavior in extended precision operations. Recall that if we wanted to check for equality of J equal to K, we subtract these two values, and if the Z flag was true after the operation, it would say that these two values were equal to each other because we produced a 0 result. Let's see how this works with a 32-bit extended precision operation. So here are two 32-bit numbers. They are clearly not equal to each other. Let's do first a subtract on the least significant word, followed by a subtract with borrow on the most significant word. So when we do a subtract on the least significant word, we're going to produce a non-zero result, and the 0 flag will be false. It will be a 0. We're then going to do a subtract with borrow. Now, if the subtract with borrow set the Z flag in a normal manner, then when this 0 value for the most significant word was produced, the 0 flag would actually be set to a 1, a true value, and we would think that these 32-bit values are equal to each other, which is incorrect. However, the subtract with borrow instruction can only clear the 0 flag. It cannot set the 0 flag. So even though the subtract with borrow produces a most significant word value of 0, it cannot set the 0 flag. The 0 flag will remain what it was by this previous operation here, which was a 0. So at the end of these two subtractions of the subtract for the least significant word and subtract with borrow for the most significant word, we're going to get a 0 flag, a false or 0, indicating correctly that these two 32-bit values are not equal to each other. Now let's take a look at this subtraction here. In this subtraction, this most significant word subtraction produced a 0. In this subtraction, the least significant word subtraction is going to produce a 0. These two 32-bit values are still not equal to each other. So we use a subtraction operation here. We'll subtract these two words and we'll get a value of 0, which is going to set the Z flag to a true value. Then we're going to do a subtract with borrow. This operation here is going to produce a non-zero result because the subtract with borrow can clear the Z flag. It will clear the Z flag to a 0, a false value, correctly indicating that these two 32-bit values are not equal to each other. Finally, let's do a subtract and subtract with borrow with two 32-bit values that are equal to each other. So this least significant word subtraction right here will produce a 0. The subtract instruction will set the Z flag to a true. This subtraction operation right here will also produce a 0. The subtract with borrow cannot set the Z flag. It's simply going to retain whatever this Z flag was, which is going to be a 1 or a true value. And so at the end of this 32-bit subtraction, we're going to get a Z flag of true, which correctly indicates that these 32-bit values here are equal to each other. Let's go look at an efficient way of doing 32-bit increment and decrement of a variable. Here we're doing k++, where this is a 32-bit wide variable. So first thing we'll do is we'll clear W0. We'll see why we do that in just a second. Now we're going to do an increment of k. That's going to take the least significant word of k, increment it by 1, and write it back to k. It will also affect the carry flag, and we're going to need to take this carry flag and we're going to need to add it to our most significant word. So how are we going to do that? Well, we can do an add with carry k plus 2, but recall that not only does this add the most significant word of k, it also adds whatever is in W0. We need that to be a 0 because the only thing we want to add in here is the carry. We want to make sure that a 0 is added to the most significant word. So that's why we cleared W0 here to ensure that W0 was a 0. So when we did this instruction, we were adding in a 0 plus the carry that was produced by this increment instruction. If we did not include this instruction here, then when we added this instruction, this would be whatever W0 happened to be, and it could be a non-zero value producing the incorrect result. The decrement operation here is going to be essentially the same approach. We're going to clear W0 first. We're going to decrement the least significant word of k and write that result back to k. Then we're going to do a subtractive borrow the most significant word. That's going to take the borrow that was produced by this decrement instruction and subtract it from the most significant word. By clearing 0, we'll also make sure that W0 has a 0 in it. So let's reinforce these concepts by looking at another example of an increment and another example of an add. So in this case, we're going to assign to k j plus 1. Notice that only k is modified, j is not modified. So first of all, we're going to do our least significant word operation. We're going to increment j and place the result in wreg. This is incrementing the least significant word of j and placing that in W0. We're then going to move W0 to k, so the end result is that our least significant word of k is equal to j least significant word plus 1. This move leaves the flags unaffected, so the carry that was set by this instruction here is still available. We now need to add this carry to the most significant word of k to complete the operation. First, we'll clear W0. This clear operation does not affect the flag, so our carry will still be valid. We're then going to do an add with carry to k plus 2. That's the most significant word of k. So we're taking the most significant word of k, we're adding 0 to it, we're adding wreg to it, which we just cleared to 0, and we're adding whatever the carry flag is as set by this increment instruction. Now let's take a look at this example here, which takes two 32-bit values j and p, adds them, and places the result in k. We're going to use a conservative 3 operand add approach. We're first going to do the least significant word here. We're going to move the least significant word of j into W0, move the least significant word of p into W1. We'll add those together, place the result in W0. Then we'll copy W0 to k, and we've just computed the new value of k least significant word. At this point, we need to do the most significant word operation. So we'll move the most significant word of j into W0, the most significant word of p into W1. We'll do an add with carry. This add, the carry produced by this add, is still valid because these moves here do not affect the status register. So we'll do an add with carry here and place the, W0 plus W1 and place the result in W0. We'll then copy the result of W0 into the most significant word of k, which is equal to j most significant word plus p most significant word plus the carry produced by this add instruction. Let's now examine 32-bit shift right and shift left. We'll first take a look at the shift right operation. We'll want to shift the most significant word first using a logical shift right instruction. This is going to shift a 0 into the most significant bit of the most significant word, and the least significant bit of this most significant word will be shifted out and stored in the carry flag. This is important as we then need to shift the least significant word right using the rotate right with carry flag. This will take the carry flag and rotate that in to the most significant bit of the least significant word, while this least significant bit will rotate out and into the carry flag, which we don't really care about. The key thing is that this instruction sequence here will capture this least significant bit falling off the end here into the carry flag, and then move that into the most significant bit of the least significant word. So here's an example of the code sequence. We're going to take K and we're going to shift it to the right by 1 position, where K is an unsigned 32-bit variable. So first of all, we'll do a logical shift right of the most significant word. This will do the shift and then place the result back into memory location. Then we're going to do a rotate right with carry of the least significant word. The shift left uses a similar concept, except it's going to shift the least significant word first, followed by the most significant word. We'll shift the least significant word first using a shift left instruction. A 0 will come into the least significant bit, and the most significant bit of the least significant word will be captured in the carry flag. We'll then do a rotate left with carry instruction, which will rotate this carry into the least significant bit of the most significant word, and this most significant bit here will then rotate into the carry flag. Again, the key component of these two instruction sequences is that the carry flag is going to be used to carry the most significant bit here of this least significant word into the least significant bit of the most significant word. So here's the code that does this. We have K is equal to K shifted to the left by 1 position. So we do a shift left of K. That's going to shift the least significant word of K by 1, place the result back into the least significant word of K. Then we'll do a rotate left of carry, the most significant word of K. If we wanted to shift multiple positions, for example, if this was K shifted to the left by 3, all we would do would take this 2 instruction sequence and repeat it 3 times. You do not want to use the shift instructions that shift by multiple bit positions, because that does not affect the carry flag. Simply take this instruction sequence and repeat it for as many times as many shifts as you need. Same thing for the right shift. If this is greater than 1, let's say it's 5, then simply take this 2 instruction sequence and repeat it 5 times.